All right, let's get straight into it. If there's one topic that's practically guaranteed to show up on your GCSE chemistry exam, it's the structure and bonding of carbon. So in this explainer, we're going to break down everything you absolutely need to know, pulled right from the AQA specification.
Okay, let's dive into this, because it's a fantastic question. I mean, really think about it. On one hand, you've got graphite, so soft it literally leaves a trail on paper. And on the other, you have diamond, so tough it can cut through pretty much anything. Both of them are pure carbon. So what on earth is going on? Well, the answer comes down to one single crucial word: allotropes. So, to really solve this carbon conundrum, we first need to get our heads around the one key definition that explains this amazing versatility. You'll see, once you understand this term, everything else about carbon's different forms is just going to click right into place.
And there it is, allotropes. It's not about having different atoms, it's about having a different arrangement of the exact same atoms. It's kind of like having a big box of Lego bricks, right? You can use the very same pile of bricks to build a tall tower or a long wall. The bricks are the same, but the final structure is totally different. And for carbon, that change in structure has some seriously dramatic consequences.
So let's kick things off with the most glamorous allotrope of them all, diamond. We're going to break down exactly how its unique arrangement of carbon atoms gives it those world-famous properties.
Okay, if there's one number you need to remember for diamond, it's this: 4. Every single carbon atom is tightly bonded to 4 other carbon atoms. This creates this incredibly strong, rigid 3D structure called a tetrahedral lattice. There are just no weak spots, only an endless network of super powerful covalent bonds.
And that structure we just talked about, it directly leads to these 3 key properties you have to remember for your exam. It's incredibly hard, it has a ridiculously high melting point, and it absolutely does not conduct electricity. These aren't just random facts, they are a direct consequence of that bonding.
So, why does it have these properties? Well, the hardness and that super high melting point, we're talking over 3,500 degrees Celsius, that's because you have to break millions of these really strong covalent bonds just to make a dent in the structure. That takes a massive amount of energy. And as for electricity, it's a total insulator because every single one of carbon's outer electrons is locked into a bond. There are just no free-moving electrons or ions to carry a current. Simple as that.
All right, now let's flip the script and see how a tiny change in that bonding pattern creates something completely different with our next allotrope, graphite. This small shift makes carbon almost unrecognizable from diamond.
Now look closely here. The new magic number is 3. Each carbon atom only bonds to 3 others. This forms these flat, interlocking hexagonal rings that look a bit like chicken wire. But wait, a carbon atom has 4 outer electrons. So what happens to that 4th one? Well, that's where things get really, really interesting.
So the properties are almost the opposite. It's soft and slippery, but it still has a very high melting point. And unlike diamond, it can conduct electricity. How can something be soft and have a high melting point at the same time? Well, you guessed it, it all comes back to the structure.
Now this is what explains graphite's split personality. That high melting point, that comes from the strong covalent bonds within the layers. You still need a ton of energy to break those. But the softness, that's all about what's happening between the layers. There are only weak forces holding them together, so they can just slide right over each other. That's literally why a pencil works. You're just scraping layers of graphite onto the paper.
And this explains what happened to that spare 4th electron. It becomes delocalized. Now that's a key exam term. You'll want to write that one down. It means the electron isn't tied to any single atom anymore. It's free to move all along the layers. And what is an electric current? It's just a flow of charge. These delocalized electrons are the charge carriers, and that's what allows graphite to conduct electricity.
This slide right here, this is your perfect revision summary. It boils down every key comparison you could be asked to make in an exam. Just notice how that number of bonds, 4 versus 3, directly leads to a different structure, which in turn determines the hardness and whether or not it conducts electricity. If you understand this table, you've mastered the core of this topic.
But wait, the story of carbon doesn't just stop with diamond and graphite. Let's quickly look at 2 more modern forms that are at the cutting edge of science, and, yep, they're on your specification too: graphene and the fullerenes.
So just try to imagine this. If you could take just one of those slippery layers from graphite and peel it off, you'd have graphene. It's a single sheet of carbon, just one atom thick. It sounds so simple, but this stuff is incredible.
For its weight, it's about 200 times stronger than steel, and it's an amazing electrical conductor.
Then you've got fullerenes, which are a whole family of carbon molecules that form these cool, hollow shapes. The very first one they found was called Buckminster fullerene, or C60 for short, and its 60 carbon atoms form a perfect sphere that looks exactly like a classic football.
And because of these unique shapes, the potential uses are just mind-blowing. We're talking about things like carbon nanotubes, which are basically rolled-up sheets of graphene being used in nanotechnology, or using the hollow cages to deliver drugs to specific cells in the body. The possibilities are huge.
Okay, so after looking at these 4 incredible forms of carbon, we can finally go all the way back to our original mystery and give the final verdict on why carbon has such a split personality.
And here it is. This is the single most important sentence for this entire topic. This is the key to section 4.2.3 of the AQA spec. It's not what an element is made of that matters most. It's how its atoms are put together. Diamond and graphite are both 100% pure carbon, but the different way their atoms are arranged and bonded gives them completely opposite properties. It's that simple and that profound.
All right, to wrap things up, here is your ultimate revision tool. This table neatly summarizes the structure and the properties that result from it for all 4 carbon allotropes you need to know. Understanding the link between that structure column and that key properties column is what is going to get you the marks in the exam.
And that leaves us with one last thing to think about. We've seen how nature arranges carbon atoms to create these wildly different materials. So, as our technology gets better and better, what's going to happen when we can start arranging those atoms ourselves, one by one? The principles you're learning right now for your exam, they're the exact same principles scientists are using to invent the materials of the future.